this problem here. Okay. Let's look at this problem here. Here's question is, here we have a function provided, and the question is asking us to use 16 by 1 mux to express this one, and also use 8 by 1 mux to express this one, and also use 4 by 1 mux to express this one. Now let's see how can we express this function using 16 by 1 mux. So to do that, 16 by 1 mux is straightforward because we have the maximum value we have is 15. So we are going to create 16 by 1 mux for that. Let's do that here. Use okay. So for this one, we are going to have 16 input and 1 output. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and start from 0. Okay, let me expand this one a little bit more so it will be clear. Okay, so I start from 0, and then this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, now let's go ahead and plug the values first. So what we do is we connect the values given with the VCC. That's basically it. So here we have 1 at 1, 1 at 1, and then we have at 3, and then 1 value at 4, and then we have 7, and then we have 12, and then we have 13, and then we have 15. What we do, we grab all of them together. Grab all of them together and then connect this one with VCC. Okay, now we connected this one with VCC, and the rest of them is going to be just connected to the ground. So this is going to be this one. Let me use a different color. This one, 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 and we grab all of them together and connect with the ground. Okay. Once now. Okay. So all these connect to the ground. Okay. That's it. This is our 16 by mux design. And once you have done that, that's it. And we also going to have the output that's going to be f of a, b, c, d. And we will have also, yeah, don't forget the control signals. That's basically the variable given. A, B, C, and the D. Okay. So that's it for the 16 by 1 mux. Now the next one is we are going to draw the 8 by 1 mux. But if you want to do 8 by 1 mux and we have 16 very like the variables goes up to 15, we definitely have to use a truth table, because otherwise it's going to be not possible. So let's create a truth table for it. So here we have 4 variables, right? We have A, B, C, D. So we are going to have 2 power 4 different orientation, that's 16. So I'm going to create a table with 16 different orientation. 1, 3, 4. Let's put 16 of these. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. Let's leave it. Make some more space. 12, 13, 14, 15, and let's use one more. Okay, now let's put our variables A, B, C, D, and then here we have the function that's given. Okay, so 16, we're gonna have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. How many we have already? 1, 2, 4, 6, 8, 10, 12, 14, 16. I had to expand this one a little bit more. Okay. Now let's put the other values. So this is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and then 0, 0, 1, 1. Then here we are going to have 4 zeros, 4, 1, 4 zeros, 4, 1, and the last one is 8, 0, 8, 1. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's it. Those are the values we are going to have. The 16 4 variable. If you have provided 4 variables, this is the 16 different orientation we're going to have. And the f function given is this. I'm going to copy this and paste it over here. Okay, let's bring this one a little bit up. Okay, here we go. Okay, now let's plug the value. So here this min terms provided, it means these are the locations that we are going to have 1. At 1 we have a 1. At 3 is 2 plus 1, that is right here. And here we are going to have a 1. And then 4 is right here, we have 1. And then we have 1 at 7, that is right here. And then we have 1 at 12. 12 is 8 plus 4, that's right here. And then we have a 1 at 13, that's 8 plus 4 plus 1, that's right here. Then we have a 1 at 15, that's this one right here. Okay, these are the ones we have, and others are going to be 0. Okay, so this is going to be how the truth table is going to look like for the given function. Now what we want to do is we want to throw an 8 by 1 mux. We have to design this given function using 8 by 1 mux. Let's do that. Let's create the mux first. Okay, here we have 8 by 1 mux. In this one we are going to have 8 input, 1 output. 1, 2, 3, 4, 5, 6, 7, 8. This location is 0, 1, 2, 3, 4, 5, 6, 7. Okay, so for the 8 by 1 what we do is we compare, like here the input is going to be the what do you call, the control signal is going to be ABC, and then we just look at CD. Actually D only, D only. So D is the only one we have to compare with the function and see how it behaves. So to do that, what we have to do is we have to group them together. We have to take 2 at a time. That's why this one is useful, because when we have next to each other, we have to take 3 ABC common factors. Like if we take A0, B0, C0, I have to take the other one also, A0, B0, C0. That is easier when we take them together. Like you can also take the A, B, D, or A, C, D, something like that. But then you have to grouping them as 0 is going to be difficult. When I do that, you will understand. So here I can group these two, like A, B, C. When A is 0, B is 0, C is 0, I can group these two together, right? 3 variable I can do together. I can group them together. So at these points, as these 3 points, how does the D act like? When D is 0, function is 0. We just comparing these two. When D is 0, function is 0. When D is 1, function is 1. So it means this the 0 output, the first location is going to be just D, because whatever the D value hold, that's going to be the output. So the first one is going to be D. And what about, so this is 8 by 1 marks, and then we're going to have the output. Let's put it F here. Okay, now the next thing is we take these two, 0, 0, 1, 0, 0, 1. Compare the D's. When D is 0, function is 0. When D is 1, function is 1. So it means this is also D. Let's compare these two, 0, 1, 0. When D is 0, function is 1. When D is 1, function is 0. This is D naught. And then compare these two, 0, 1, 1, 0, 1, 1. When D is 0, F is 0. When D is 1, F is 1. So this is also a D. Compare these two, 1, 0, 1, 1, 0, 0, 1, 0, 0. When D is 0, F is 0. When D is 1, F is still 0. So it doesn't matter if you put 0 or 1 for D, it's going to be 0 anyway. So you connect this one with the ground. So regardless of what value we put for D, it's going to be 0. So we connect that one to the ground. And let's compare these two, 1, 0, 1, 1, 0, 1. When D is 0, output is 0, function is 0. And then when D is 1, the function is still 0. So here also, regardless of what you put for D, the value is going to be 0. So you connect this one also to the ground. Okay, and let's compare these two, 1, 1, 0. When D is 0, the function is 1. When D is 1, function is 1. So regardless of what value you have for D, the function is always going to be 1. So you connect this one with VCC. So 2 things you have to remember, like if you are always getting 0, you connect to the ground. If you're always getting 1, you connect it to the VCC. Let's look at the last two. 1 1 1. When D is 0, the function is 0. When D is 1, function is 1. So this is going to be D. Okay, so this is the 8x1 mux design. That's it. And now let's see how can we design 4x1 mux. For that one also we are going to need the truth table. So let's do this one here as well. So 4x1 mux. For 4x1 mux, we are going to have two control signals. Here we can take A, B. Okay, and then output is F. This is a 4x1 mux. 4 inputs. This is 0, this is 1, this is 2, this is 3. These are pin numbers. Pin 0, pin 1, pin 2, pin 3. Okay, that's it. Now here what we have to do is we have to group it as 4. We have to just group A and B. And then we have to compare the behavior of C and D. Okay. So here what I'm going to do, I'm going to compare the 0 0 ABs. You see the like if I choose, you can choose a C here, a D here, but when you choose, these zeros are not going to be together, right? Here if I take A, B, I can combine all those 4 zeros at the same time. I can look at all of them at the same time. But if you take a D or a C here, then you have to search for the similar values to compare them. So that's the difficult part. So that's why it's better to choose the first two, whatever the value. Like if you are getting X, Y, Z or something, then X better choose X, Y, something like that. So you have to think about that. So here we are taking 4 at a time. Okay. 1 4 is 4. Okay, now let's look at this. The first one, we took care of AB, 4 of them 0, right? We are looking at AB only. Then what we do, we compare the CDF behavior. Okay, let's look at this. So here, as you see, when C is 0, F is 0, C is 0, F is 1. When C is 1, F is 0, C is 1. So it doesn't matter what value you put, F is giving all the values for C. But let's look at this D. For D, when D is 0, F is 0. When D is 1, F is 1. When D is 0, F is 0. When D is 1, F is 1. So whatever the value D have, this is giving the exact same function. So this is actually dependent on D. D is going to be the one right here. Whatever the value D hold, that's going to be their function. So we put a D for that. Now let's look at the second one. So we taken care of the first 4. Now let's look at these 4. Next 4, that's 0 1 0 1 0 1 0. So here let's compare CDE. Okay, here when we have 0 0, we are getting a 1. When we have 0 1, we are getting a 0. When we have 1 0, we are getting a 0. When we have 1 1, we are getting a 1. So this is acting similar to a logic gate that we know. If you remember this one, XOR gate, it looked like this. XOR gate, okay. So what is the truth table for XOR gate? The truth table is A, B, and the output. When we have 0 0, the output is 0. When we have 0 1, the output is 1. When we have 1 0, the output is 1. And when we have 1 1, the output is 0. Now let's compare this. 0 0, we have 1. That is opposite to this. When we have 0 1, we have 1 here, but here is 0, opposite to that. When we have 1 0, here we are getting 0. Here it's opposite to that. When we have 1 1, we are getting a 0. That's opposite to that. So what we are going to have is XNOR gate, because XOR gate is this. XNOR gate is an opposite to this. So here we have to just connect an XNOR gate with this. Okay, this is actually just one, I think. Yeah, XNOR gate, like you have to put a not at the end. You see, I put a circle like this. That's XNOR gate. That's gonna have the exact same output as this one. So here we just connect the C and D, C, and we are gonna get this outputs like that. Okay, now let's look at these four: 1 0 1 0 1 0 1 0. When 0 0, we are getting 0. When 0 1, we are getting a 0. When 1 0, we are getting a 0. When 1 1, we are getting a 0. So here it doesn't matter what we have here, we are always getting a 0. It means we just connect this one to the ground. Connect this one to the ground. Let's look at this one. Let's group this 1 1 1 1 1 1. So when we have 0 0, we are getting a 1. When we have 0 1, we are getting a 1. When we have 1 0, we are getting a 0. When we have 1 1, we are getting a 0. When we have 1 1, we are getting a 1. So here you can use any logic gate you can think of and try to come out of the solution. But the one I am seeing here is, if you put an OR gate with C naught in it and D connected, you're going to get the same output as this. Let's look at this. So if 0 and 0, if you put a C naught, this is going to become 1. 1 or 0, what is that? That's 1. And here 0 1, and if I put a naught, this is going to be 1 1. 1 or 1, what is that? 1. And here if I put a naught, this is going to be 0. 0 or 0, what is that? That's 0. And if I put a naught here, this is 0. 0 or 1, what is that? That's 1. So this one works. And that's basically it. That's how we can decide the exact same function with a 4x1 mux. We can do that with we can design with that one with 4x1 mux as well. And that's it for this video, guys. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.